Okay. Well, thank you very much for the invitation. It's very nice to be in Montreal. And so, yeah, today I'm going to talk to you about Ricci flow in dimension 4. So I want to advertise this topic because I think that's very promising and a lot of, it has a long history, of course, but some newer results give it some more reasons to be studied. And so the works I'm going to present today mostly are collaborations with Alex Deruelle in Paris and Tristan Naff at MIT. Okay, so what is maybe the motivation for all of this? Well, this is this dream of a geometer, maybe the biggest question in geometry, which is given a topology, so this flexible shape, can I find a best geometry, which would be one of the shapes it can take? So why do we care about this? Well, let's look at this picture. Here it turns out that we have two very different geometries. They really don't look the same at all, but it turns out that they have the same topology, which is that of the two-sphere. But obviously, it's much easier to recognize the two-sphere from the picture on the right. And so that's why we care about finding better or simpler geometries, because it's easier to recognize a topology when we have a better geometry. And so that's the whole idea of Ricci flow. And oversimplifying the rest of the talk, the best geometries we'll try to find are Einstein metrics, and Ricci flow will try to optimize the geometry for us, and we'll be looking for these Einstein metrics. Okay, so what does Ricci flow do? So let's look at dimension 3. So I told you we'd like to find the best geometry, but generally you cannot find one best geometry in your whole topology, at least from dimension 3. Instead, what you can do, and that's what was called Thurston's geometrization at first, is that you can decompose your manifold along tori and quotients and spheres and quotients, and between these regions, so on these regions with boundary, if you want, you can find some optimal geometry. So you decompose M into MIs, into the MIs here, and each MI will admit one best geometry, and all of these best geometries are classified. And Ricci flow does that for you. So Ricci flow provides this decomposition in dimension 3. And Ricci flow has two stages. The first stage is finite time singularities. So it's maybe the most challenging part in dimension 3, at least. And topologically, when you have a finite time singularity, you will just cut your manifold along a two-sphere or a quotient. Eventually, you don't have any more of these finite time singularities. So this is a very hard result, but it's been proven. And eventually you get a flow that exists for all times or has completely disappeared. But let's assume that there is still something remaining. Then you have a flow that exists for all times, and its behavior at time infinity is that there will be regions which carry all of the volume, which are called the thick regions, and they approach some hyperbolic metrics. So you will find hyperbolic metrics with cusps, and other regions which are collapsed in comparison, which we call the thin regions. And so in the long-time behavior, you will have separations between these thick regions and thin regions, and they will correspond to cutting the manifold along tori and quotients. So that's a beautiful picture. It does the geometrization for you, and we'd like to extend it. So what could be maybe a dream in dimension 4? Well, in 2000, Yao asks if any 4 manifold can be decomposed similarly into pieces which carry Einstein metrics, which generalize these thick regions, these thick hyperbolic parts, and other parts which would be circle bundles over 3 manifolds and surfaces bundles over surfaces. Well, that's a very bold question in 2000, especially before the actual result in dimension 3 was proven, but that gives you what kind of result we're looking for. And so that was a bold conjecture in 2000, but recently Bandler gave us some good reason to believe that Ricci flow could achieve something like this. Maybe not as clean, but Ricci flow should decompose our 4 manifolds, and it does it under between quotes here. It does it in a weak way. So in a weak sense, Ricci flow will decompose your 4 manifolds, and the main pieces, again, the ones that you find at time infinity, will be the Einstein metrics, which generalize the hyperbolic regions. And so, Ricci flow has some potential in dimension 4 as well. So, okay, in all of these pictures, the main pieces are Einstein metric. So let me motivate them. So an Einstein metric has constant Ricci curvature. It's probably the first equation you've seen in Riemannian geometry. And it's a nice elliptic equation because in good coordinates, the Ricci curvature looks like a Laplacian of the metric. But my favorite way, so it's already a constancy of a curvature. So it gives you that you're looking for particularly homogeneous metrics. But my favorite way to motivate Einstein metrics is four-dimensional. And Einstein metrics, when they exist, minimize some complexity. So my complexity will be the L2 norm of curvature. And the least curved geometry, the better, the simpler the geometry. It turns out that on any manifold, there is a topological lower bound. So this bound here does not depend on the metric. So for any metric G, you have such an inequality. And the equality case is exactly when you're Einstein. So whenever they exist, Einstein metrics are the absolute minimizers of the L2 norm of curvature. So that's my favorite way to motivate Einstein metrics in dimension 4. They are the simplest in that sense. And so we would like to understand them. And we would like to use Ricci flow to find them. And so that's also only in dimension 4 that I think Einstein metrics are really motivated. In higher dimension, they tend to be too complicated. There are too many of them. They develop very complicated singularities. And so we cannot deal with Einstein metrics from dimension 5. And so obviously we won't be able to deal with Ricci flow from dimension 5. So let me talk about Ricci flow to tell you maybe what's the link with Einstein metrics. So Ricci flow is a curve of metrics. So it evolves a geometry and it homogenizes it. So it's homogenized by this parabolic equation. So it's a kind of heat flow locally on the metric. So locally, it's really homogenizing everything like a heat flow does. But globally, there are maybe more problems. There could be singularities, and that's where the difficulties come from. But that's what Ricci flow is. And I'll talk during this talk about the renormalized Ricci flow, where instead of just -2 Ricci, I'll have this minus lambda G. And you see that for this flow, the fixed points are exactly Einstein metrics. That's when the right-hand side vanishes. And this is just the same flow up to rescaling the metric by some factor, depending on lambda. It's really nothing is happening geometrically. It's just a way to make it. I just want to point out right now that I'm going to talk about the renormalized Ricci flow. So this flow has, it's hard to overstate how important it's been for geometry and topology. But if you look at the results on Ricci flow, they tend to be of one of two kinds. They are either three-dimensional only, or they hold in every dimension, but under strong assumptions, usually. And so what's missing is, well, a theory in dimension 4. So what can we do with Ricci flow in dimension 4 specifically, without some of these very strong positivity assumptions on the curvature? So that's a long-term goal. And we could ask, well, why are we doing that? And so, well, why dimension 4? Well, it's the next one after 3. That's the first good reason to look into this. But, even if we were, and the next reason is that it's probably the last dimension where we can say anything anyway. Dimension 4 is also where most questions are open in topology. That's a very unique dimension topologically. And for all these reasons of being so unique topologically, but also geometrically, there are many specific theories in dimension 4, or theories that exist in every dimension have very specific behaviors in dimension 4 for various reasons. But a lot of theories intersect in dimension 4 because it's a multiple of 4, it's a multiple of 2, it's 2 plus 2. There are many reasons for everything to happen at the same time in dimension 4. And so there is a rich variety of techniques and theories to use in dimension 4. So that's also one thing that we're interested in. We want to use all of these techniques along Ricci flow to maybe hopefully understand it better in dimension 4. So maybe a more concrete question, which is a distant goal, is this big conjecture in topology, which is the 11-8 conjecture. So this is a very big conjecture because if proven, that would complete the classification of smooth, simply connected four manifolds up to homeomorphism. So that's really a big conjecture. People have been trying to solve it for a very long time, and it's the techniques that are known in topology right now fall short of proving this this inequality, and it seems that Ricci flow could be a good strategy towards it. Let me maybe say a bit more about it. So the conjecture, so it's 40 years old, a bit more, but it asks whether on a four manifold that has all of the good properties, in particular it has to be spin, it asks whether an inequality is satisfied between the second Betti number and the signature of the manifold. I note that there is equality when you're on the K3 surface, and that the inequality with 10/8 is known, and maybe 10/8 plus 2 or something a bit better than 10/8. But I think I've been told by people in topology that recently they proved that by all of the techniques they know, there is no way they can get better than 10/8 here plus 4, I think, or something like this. So they won't be able to, by the current techniques, to prove the actual inequality that would complete the classification of four manifolds to homomorphisms.
There's really a big difference between 11/8 and 10/8 in terms of classification.
I mean, there is just a gap. They know everything that happens if we are over 11/8. They have the classification, but they don't know if some manifolds can be between 10/8 and 11/8, and they know everything else will be of the type they know, so they will be connected sums of K3 surfaces, S2 times S2, and they have a bunch of, I mean, they have a classification that's quite clear, but yes, there is a big gap in the sense that, well, they just don't know. They know everything except for this tiny, I mean, it seems tiny, but it's, I don't know really how large it is. But so yeah, that's what we want to prove. And so why would Ricci flow make sense? Well, the thing is that so we want to prove such an inequality. So mostly we want to understand the signature. It's the most challenging part, and so we want to show that the signature is small. And so along the Ricci flow, if you remember, there are two stages, finite time singularities, but these tend to have positive scalar curvature. And positive scalar curvature, at least on the closed manifold, gives you that you have zero signature, because I'll say more about this towards the end. But so this is good for us, because up to maybe boundary terms, we will have zero signature, and the inequality is obviously satisfied. In infinite time, we'll have most of the regions will look Einstein at some scale, and the Einstein metrics also satisfy a better inequality than what we need with 12/8, and so we will be good as well. On the Einstein pieces, the conjecture is satisfied for these metrics, but there remains difficulties, because there are some singularities that can form orbifold cusps. There are collapsed regions as well at time plus infinity. So the behavior at time plus infinity is probably the most challenging part, and another part that will be quite challenging is the boundary terms that appear at these finite time singularities and also at infinite time that really change this signature. But the key point, maybe the thing that makes it believable, is that in all of this strategy, and if we count the main difficulties, we don't need to classify Einstein metrics or Ricci solitons, which seems to be really far away. But so to prove this, we don't need any classification result, because we would use either this inequality or the fact that we have positive scalar curvature. We would bypass maybe the very hard work that would be classify Einstein metrics. So this conjecture might be approachable in a reasonable time. So that's our motivation at the moment for Ricci flow in dimension 4. And so let me explain what I've not been working directly on this, but I want to present some techniques that are specific to dimension 4, and that will tackle some of the simpler difficulties here. So we'll talk about the orbifold singularities mostly today. So let me give you maybe a brief overview of the story for Einstein metrics first, and then we'll move on to Ricci flows. So for Einstein metrics, you want to use the Gromov-Hausdorff distance. So it's the most general distance you can take for metrics with lower bounds on Ricci curvature, and so in particular Einstein metrics. And it's a very good distance because it has very good compactness properties. So if you take a sequence of Einstein metrics, if it has bounded diameter, then it always subconverges to something which is an Einstein orbifold. So it's as close as you can get to a smooth metric. It's the nicest type of singularities. And so in dimension 4, and that's the big difference between dimension 4 and higher dimension, the singularities are very simple. But maybe what was missing in the 80s when this was proven is that the Gromov-Hausdorff distance is really too weak for any kind of application. You don't know anything about the topology of your metrics. It doesn't tell you that much about this degeneration and all of its properties. So let me talk about these singular metrics. So an Einstein orbifold is a metric that's just smooth everywhere, except at a finite number of points where up to taking a finite quotient, it's just a smooth metric. So really there is nothing too complicated about these metrics. They are the nicest singular metrics you can imagine. And so the simplest examples are quotients of the Euclidean space. And the simplest examples of these is the antipodal identification of x and minus x for every x in R4. And I call this singularity R4 mod plus minus. The next simplest example is a quotient of the sphere in the same way where you do this antipodal identification in geodesic chart, if you want, starting at one of the two poles. And you obtain this orbifold, which is the American football metric with two singularities R4 mod plus minus. And if you quotient also the torus, the 4 torus, you will obtain 16 singularities R4 mod plus minus. So these are the simplest examples of orbifolds, and I'll just talk about them today. So the singular spaces are really not that bad, but the way they appear is also not that bad. Because the way the singularities appear is by blowing down some bubbles, which we call Ricci flat asymptotically locally Euclidean metrics, which just means that there are Ricci flat and asymptotic one of these quotients of the Euclidean space. And today I'm just going to talk about the simplest example, which is the Agush-Jensen metric, which is asymptotic to the simplest cone R4 mod plus minus. And the way the singularities appear is simple because it's just a rescaling of this metric. And that's what it looks like, at least. You start with your Agush-Jensen metric, you rescale it by a small factor epsilon that you let go to 0. By definition, you converge to the asymptotic cone, and here, just here, you've created a singularity. And that's how the singularities appear for Einstein metrics. And so that's why we have hoped to understand them fully and to reconstruct them by a procedure that's known as gluing perturbation. So for this, you take one of your one bubble and one orbifold, and you glue the two together if they have the same cone as follows. So you first rescale your bubble so that it looks like the cone, and you take the region of your orbifold that also looks like the cone, and you glue the two metrics together by having on the left-hand side just your bubble metric, on the right-hand side just your orbifold metric, and in between you just interpolate by a cutoff function. So it's really a dumb way to glue the two metrics, but this still gives you a metric which is almost Einstein. So it's actually Einstein everywhere in the white region, and the green region, it's very close to being Einstein. So we're very close to being Einstein, and you're asking, well, can I actually make it Einstein by perturbing it? And that was done maybe since the 80s, and it works in some situations. The simplest, maybe the most famous, not the simplest, but the most famous example is the Kummer construction on K3. So you take this quotient of the torus I presented, and you glue a bunch of Agush-Jensen metrics in the same orientation, and you might even glue them at different scales and rotate them by some rotation phi j here. And as long as all of the bubbles are glued in the same orientation, you will always be able to perturb this to a Ricci flat metric and actually a hyperkähler metric. So it works in some situations. So that's a very nice procedure when it works. But there is always a gap when you're doing that. There is always a gap between the general type of degeneration, which is Gromov-Hausdorff, which is extremely weak, and whatever you're constructing, which will always be in some very specific holder space, weighted holder space. And so there is a big gap between this very weak convergence and this very strong convergence. And so during my thesis, I started by bridging the gap between these two convergence, because if you had the assumption that you're Einstein, then actually converging in the Gromov-Hausdorff sense is equivalent to converging in some weighted Holder space. But the weighted space here is more complicated than the usual ones. But still, it gives us a way to really reconstruct every Einstein metric, and we reconstruct them as in this picture below, but let me explain what I mean by this picture. So instead of always finding Einstein metrics, what you can always do by gluing perturbation is obtain what I call an Einstein modular obstruction matrix. So that means that you're not quite solving the Einstein equation, which would be this is equal to 0, but you have an obstruction, which is in some finite dimensional space, which is essentially the co-kernel of your linearization. So if you're familiar with Lyapunov-Schmidt reductions, it's really what's happening here. And maybe for people used to moduli spaces, this is a Kuranishi map close to a singular metric. So it was known close to a smooth metric. It's a result from the 80s, but approaching a singular metric took a long time. And so what it gives you in the end is that of the moduli space of Einstein geometries, so which are these darker purple lines here, can be embedded, can be put in a finite dimensional box of Einstein modular obstructions metrics. So it first tells you that the dimension of the moduli space cannot blow up close to a singular metric. And it tells you that you have a nice, somewhat nice set of Einstein metrics. And one thing that we cannot rule out is the accumulation of different connected components of the moduli space at a singular metric. But other than that, we have a quite nice structure. And so we embed our Einstein metrics inside the set of Einstein modular obstructions metrics. And in particular, we reconstruct every single Einstein metric by just gluing perturbation procedure. And that lets us approach every single Einstein metric that's approaching an orbifold with any precision you want. That's very helpful in different directions, which I won't talk about too much today, but maybe just one thing, which was that these obstructions are actually important. And one old question was, well, okay, every Einstein manifold, when it converges to an Einstein orbifold. But what about the converse? If I take an orbifold, can it be a limit of Einstein metrics? So I showed that no. Actually, the simplest orbifold, S4 mod Z2, cannot be a limit of Einstein metrics. And hyperbolic orbifolds cannot be limits of Einstein for manifolds. And so the obstructions are really there, and they have to be there. And so today, what I want to talk about is that when you have obstructions, it tells you something about the Ricci flow. So maybe a picture before that. So one thing that you might have tried, so it makes sense to try this to construct a new Einstein metric. You take this quotient of the sphere, and you glue the bubbles that correspond to the singularity. So you glue two Gucci-Henson metrics, and you try to perturb this here to an Einstein metric. And what I show is that it's impossible to do that. And it's not only for Gucci-Henson, but for any bubble here. You glue whatever you want. It won't be possible to perturb it to an Einstein metric. So let's keep this, let's have this picture in mind for the rest of the talk, because that's going to be our main example. So let me now talk about orbifold singularities along Ricci flow, and what's the link with these obstructions to being Einstein. Okay, so orbifold degeneration occurs along Ricci flow. Okay, that's why we care about it. But maybe more importantly, orbifold singularities appear at the two main stages of Ricci flow. So at finite time singularities, the singularity models will be Ricci solitons, which is an extension of the Einstein equation. You just have this Hessian here. And but they are orbifolds. So for instance, S4 mod Z2, which cannot be desingularized by Einstein metrics, is a possible model of a finite time singularity, and Bandler's theory tells you that it's a very possible singularity model for Ricci flow. And in the second part, they also are showing that the thick part of a long-term Ricci flow in dimension 4 is an Einstein orbifold, such as a hyperbolic orbifold. And so we want to understand how these occur and when they occur or not. And so maybe again, this is maybe the analog of this theorem from the 80s. And this is only true in a very weak sense, which Bamler calls F convergence. And this is, again, too weak for application. So we will again have a gap between what we construct and what's been proven generally. So I'm trying to summarize this whole section in one picture. So what we're saying is that, well, the Ricci flow, the renormalized one at least, is if you start it at one of these Einstein modulo obstructions metrics, then it tells you that the evolution of the metric is essentially this obstruction. So that's the observation that we make, and that helps us a lot. Because now you can go back to your moduli space that you embedded in these Einstein modulo obstructions metrics. And it turns out that this -2 times the obstruction really gives you the dynamic of Ricci flow. So what we are trying to say today is that if you start a Ricci flow at any metric, then at leading order, Ricci flow will just be following the ODE given by the vector field. And so having the arrows pointing inwards will tell you that you're stable. You flow back to your orbifold. Having them outwards, then it will tell you that you flow away from your orbifold and you're unstable. And so that's the source of this notion of stability of orbifolds that we introduce. So maybe the key point is really that the obstructions determine the Ricci flow. So what is the usual situation? Well, the usual situation is that you can construct an Einstein modulo obstruction metric, and the obstruction is of a very specific type. It's some number times a deformation that corresponds to just growing or shrinking the bubble. So at leading order, really, the Ricci flow, the renormalized Ricci flow, only modifies the metric in the bubble region and will evolve it according to making the bubble grow or shrink. That's the only thing that Ricci flow is doing at leading order. And if you just do your simple chain rule here, you'll see that the size of the bubble evolves by this very simple ODE, and so it will be either grow or shrink exponentially fast when gamma is not 0. So that leads us to, so this evolution here leads us to this definition of stability and instability. So we'll say that we are stable if gamma is positive, and so if the bubble shrinks in infinite time exponentially fast, so the bubbles shrink, so you go back to the orbifold. In the previous picture, the arrows would be pointing inwards. And this is caused by having negative curvature at your singular point. Similarly, when gamma is negative, then the bubble grow and you're flowing away from the orbifold, and so you will be unstable, and that's caused by positive curvature. Maybe one, I think, interesting observation is that you can say much more about the dynamic if what you're gluing is one of the known examples of Ricci flat AED metrics, namely quotients of Kronheimer's instantons. Well, all of these instantons are parameterized by what's called the period map, which is composed of a number of vectors in R3, essentially. And the evolution of these parameters is by, again, at leading order, by this very simple ODE that the parameter will evolve by just the exponential of your self-dual curvature. So you take your curvature and you restrict it to the self-dual part. And the evolution of Ricci flow is really given by just this 3x3 matrix here. And that's a very clean and simple result, but it tells you when the bubble will be flowing back to the orbifold and when it's going to be growing. And so you see that when R plus is positive, then you'll be growing. When R plus is negative, you'll be shrinking. And so that leads us to this definition that you're linearly stable when you have negative curvature at your singular point. And if you are gluing Kronheimer's instantons, then the condition is only on the self-dual part of curvature. So maybe to illustrate that when you're not linearly stable, I want first, to talk about the Ricci soliton setting. But so that's for Einstein metrics. An Einstein orbifold is linearly stable if there is this condition. So with the curvature R. But if you have a soliton, then you need to slightly change your curvature to this one, which is R bar plus, which was introduced by Cao and Tran. And it's a slight modification of the usual curvature by the scalar curvature, but doesn't, I mean, it changes things, but just on the way, we also prove that Ricci solitons cannot always be desingularized by Ricci solitons, but this is not really our focus, but that's how we get this new this condition here. And so, yeah, what I wanted to say is that we can illustrate this on this S4 mod D2. So S4 mod D2 has positive curvature. And so by this criterion I gave you, the bubbles will be growing along the flow. And indeed, with Alex, we construct an ancient Ricci flow starting at this orbifold and many others where the bubbles are growing. And so Ricci flow by itself desingularizes your orbifold. And you have an ancient flow and shows that the bubble is unstable because the flow is flowing away from the orbifold. And this ancient flow also shows, I mean, gave some examples of things that we didn't know. So it has pinched positive Ricci curvature and seemed possible in dimension 3 and was not known if it existed from dimension 4. Well, it does. And it has bounded self-dual curvature and traceless Ricci curvature, which is, so everything is bounded except W minus, and that's the only thing that creates the singularities you see at time minus infinity. So maybe one word about the idea, but really we are starting with an almost Ricci flow, and we try to perturb it to a true Ricci flow. So it's really the analog of the gluing perturbation. It's actually a gluing perturbation, but in the parabolic setting. So we again need to use some weighted Holder space, and a big motivation for us is a paper of Deruelle and Capullas that exactly achieved this. I'm going to say more about this in a slide or two. But this is they really developed a lot of the analysis we use. But so maybe to give an idea of why here we can solve, we can replace obstructions by growing or shrinking the bubble. I want to say that we can kill the obstructions up to modifying our geometry. So the idea is that, well, let's take a Laplacian, maybe a Laplacian plus some curvature term. And the idea is that usually when you take a right-hand side psi, if you want to compensate it, you can only do it up to a cokernel. So let's take just a right-hand side, and usually you can only find a two tensor, or well, here it's a two tensor, but it could be, it works for many other situations, but your usual Lyapunov-Schmidt reduction at the linear level just tells you that you can solve orthogonally to the kernel and modulo the cokernel, right? That's the usual way you solve your equations because you cannot do better. And so usually, so in the elliptic setting, sorry, you cannot do better than this, and that's why you can only solve the Einstein modulo obstructions equation. But when you have a flow, you can instead take this and see it as, well, you see, L of G of O of T is just 0. So this is really dt of OT is really this O prime of T. And so you can trade this obstruction here on the right-hand side for a modification of your H on the left-hand side. And so in the end, you can always solve the equation without any obstruction, but at the cost of not solving orthogonally to the kernel, but adding this evolving element of the kernel. And so that's really what makes Ricci flow much more flexible than the Einstein equation with respect to the obstructions. So we think that this is important because we think that this is the only way an orbifold singularity can occur along Ricci flow. So that's our main conjecture. And maybe two consequences would be that S4 mod Z2 can never appear along Ricci flow while it was a valid singularity model by Bandler's theory. And the other one is that hyperbolic orbifolds, for instance, are stable and they should appear as these thick pieces, but even the singular ones, and that's the new part. And so we hope to construct some of these immortal flows in the near future as well. So maybe to show that we recover some older constructions, well, Deruelle and Capullas constructed something that looks a lot like a Kummer construction, but this time they glued some Egush-Jensen metrics in the negative orientation and some in the positive orientation in a very symmetric way. And they showed that there is an ancient Ricci flow that starts at this orbifold and makes the bubbles grow. And so that's really what was our motivation and our inspiration. And there is a way to interpret this, even if the orbifold is flat, as a positivity of the curvature at the singular points. And so if we push our analysis at a higher order, then we recover the results. But I should say that their result relies a lot on symmetries and is a very unstable situation. If you glue in any other way what they are doing, you will not find an ancient Ricci flow. And so they really use a lot their symmetries. And it's a very specific Ricci flow that they find. Another situation that we recover, something that was the first time someone exhibited some orbifold singularity formation along Ricci flow, and that was Appleton, a student of Bamler, who quit math since then. But he worked on Ricci flow in a cohomogeneity 1 setting, and he developed a Ricci flow that looked like an Gaussian metric glued to a quotient of a Ricci soliton called the Bryan soliton, glued to a cylinder. And it turns out that, at least numerically, the scale of the Gaussian metric was at the singular time was much smaller than the scale of the Bryan soliton, meaning that the Gaussian metric, the bubble, was shrinking much faster than the next scale, meaning that this should be stable in our sense, because the orbifold was shrinking compared to this Ricci soliton orbifold. And indeed, with our condition, we see that the Bryan soliton, despite having positive curvature, its modified curvature is negative, and so it's a stable orbifold in the Ricci soliton sense. And so we recover this numerical observation with our definition, and we have such a simple definition, which is just, well, look at the curvature at your singular point, tell me if it's positive or not. That you can apply it to a bunch of situations and a lot of the known examples, and you can just check if they have this positive or negative curvature, and you can classify them into stable and unstable orbitals. So the stable ones should always appear in the long-term behavior or at singular times, but the unstable ones should not. So that's the first thing I wanted to talk about today. So it's 4-dimensional because orbifold singularities appear in dimension 4, and that's when we can understand them. So that's why it's only in dimension 4 that we'll be able to do that. And the second thing I wanted to talk about is one of the main specificities of dimension 4, which is self-duality. It comes from a group theoretic anomaly. That the group of rotations, SO4, is not a simple group, not a simple Lie group, while in every single other dimension, it is a simple Lie group. So from this point of view, geometrically, dimension 4 is very different from other dimensions. There are many other ways in which dimension 4 is a very unique dimension, but that's the one I pick for today. And at the Lie algebra level, it tells you that the two forms decompose into two parts, both of dimension 3. So this is all very algebraic, but geometrically it means something. It means that you can make sense of these two 3-dimensional pieces as being the eigenspaces of the Hodge star, which depends on the metric. And so you can define two bundles, two sub-bundles, lambda plus, lambda minus, which will be your self-dual 2 forms and anti-self-dual 2 forms. So the first way it's been used is to decompose the curvature of metrics in dimension 4, and that's something that can only be done in dimension 4. And that's the first thing that is quite useful. So you can decompose your curvature. So by the way, it gives you finally a definition, a true definition of this R plus, but it's really what goes from lambda plus to lambda plus. And all of the other parts can also be understood. And so you can really decompose your curvature in here through this direct sum, and you see in particular the traceless part of Ricci. So if you're Einstein, then these off-diagonal terms are all 0, and so you just end up with 2 blocks here. And so that's a nice observation, but we would like to go a bit further And our motivation was an old question, because along Ricci flow, there are not that many curvature conditions that are preserved, but the largest one in except positive scalar curvature in dimension 4 is essentially this one, that the R plus, so just this part on top, is positive. And so you'd want to understand what happens to a Ricci flow that satisfies this property, because it will be preserved by the Ricci flow. So what makes it difficult to handle by usual maximum principal arguments is that, well, the evolution of R plus is nice. If you assume that R plus is positive, this is positive, this is positive, this is positive. This is a bit annoying, but this is positive, right? But the traceless part of Ricci, which is what you'd like to control, is not well behaved, because in its evolution, you see some anti-self-dual part of curvature. And so if you don't know that, for instance, the anti-self-dual part is also positive, then you cannot say anything, because this term is very bad. This term is quite bad as well, but at least it's only involving Ricci, so you might be able to say something about it. But so our idea with Eaton was, well, is there maybe a way to get rid of this bad term and say something about these flows? And so the observation towards this is that the bundle of self-dual 2 forms determines your conformal class in dimension 4. And if you fix a volume form, then it completely determines your geometry, your metric. And so really you can rewrite a Ricci flow as just saying what happens to the bundle of self-dual 2 forms. So, well, let's try to see what it could look like. So, well, the Levi-Civita connection that you project on lambda plus, I'll call T of G. And so it's lambda plus valued 1 form. And its curvature is F, which is a lambda plus valued 2 form, which I can decompose into a self-dual and anti-self-dual part. And that gave me F plus and F minus, right? So I can always do that. But the key observation is that this F plus up to a constant is the self-dual curvature that we had before. And then the anti-self-dual part is the traceless Ricci curvature. So it's an old result, but it's a beautiful observation in dimension 4. And for us, the key point is that we don't see this R minus, we don't see the anti-self-dual part of veil. So that's why we hoped that maybe we could get rid of this bad term that we saw in the previous equation. And maybe as another remark, this FG here is self-dual. So this vanishes exactly when you are Einstein, so when the traceless part of Ricci vanishes. And so Einstein metrics are really the instantons in the Yang-Mills sense of this theory. So that's really a beautiful observation for Einstein metrics, but here we're extending it to Ricci flow. So, well, let me first answer this previous question. Unfortunately, we don't find a way to actually use these equations, but they are still much nicer than the previous ones, because we got rid of the W minus, but we also got rid of the bad R plus sharp and traceless Ricci sharp terms. They are traded for some Hodge Laplacian here. So you can see that as a Weizenbach formula, but we knew what we would get before even using the right Weizenbach formula here. And so these new formulas are well adapted to integration by parts. And so that's what we tried. And we found some other useful facts that Ricci flow, not Ricci flow right now, but just in a minute. So take a variation of the metric and consider the variation of the connection associated, and look at the evolution of the L2 norm of curvature. So I told you it's adapted to integration by parts, so it's easy to understand the evolutions of squared norms of tensors. So if you look at this, then you get that the leading term is some connection, is your variation of the connection against this here, plus some terms that don't involve any derivative of the metric. And the key point for us is that Ricci flow is the only metric deformation that makes it look like a gradient flow. So the only metric deformation that gives you this variation of the connection at leading order is Ricci flow. And so in that sense of leading order being the derivative you take, Ricci flow is the closest you can get to gradient flow of the L2 norm of curvature at this level. So with a second order variation of the metric. And so along this specific derivative, this formalism lets you very easily compute the evolution of the L2 norm of curvature. And if you remember, the L2 norm of curvature is very linked to the underlying topology. And so the evolution is as follows. So it's just the L2 norm of curvature and decompose in a term that has a good sign and this lower order term I mentioned, which is just, Ricci against Ricci. So that's a positive matrix. It's really a 3x3 matrix against a 3x3 matrix. It's really not something completely crazy to compute. But this term can be bad, actually. If you take S3 times S1 or S2 times T2, then this term will be more important than this one, and this can blow up in finite time. But at least it tells you what you want to control the L2 norm of curvature. And when you control the L2 norm of curvature, usually you understand everything. At least in the Einstein setting, that's how it works. So yeah, we want to, so up to understanding this term, we have a better understanding of the L2 norm of curvature, and we hope to use it in different ways. But in any case, Ricci flow really looks like a Yang-Mills flow at leading order. And so there are people who know a lot about this Yang-Mills flow and are trying to apply these formulas to Ricci flow now. Okay, so what I wanted to say today is really that I mentioned before, we have specific tools that have yet to be applied to Ricci flow. And so as a conclusion, the first thing we looked into was how do orbifold singularities appear along Ricci flow? Well, with Alix, we explained this by a notion of stability for the orbifold singularities, and give one explanation of the formation of orbifold singularities. Hopefully, we think that this is the only way they can appear, and the two conjectures we have are this one that S4 mod Z2 can never appear, and that the hyperbolic orbifolds always appear. But obviously, this would extend to many more metrics, but these are the simplest ones I can think of. And so maybe to come back to this 11.8 conjecture and other things we're doing towards this, well, thanks to the classical index theorem, the signature is the index of the Dirac operator, and the Euler characteristic is also the index of some Dirac-like operator. So what we'd like to do, for instance, is to use these elliptic operators, the Dirac operator and the D plus D star, in harmony with Ricci flow. So we would like to evolve them with Ricci flow and understand their properties along Ricci flow. So the idea we have is to adapt this to the weighted setting with weights that we can choose. So let me explain here. So a weighted manifold is really a Riemannian manifold which has a bit of a different measure than the Riemannian measure. And this was really the core of Perelman's proof. We introduced a weighted scalar curvature and introduced an entropy, which is really the Hilbert-Einstein functional, but in the weighted setting, if you want. And Bandler's theory also relies on this weighted setting. And so this weighted setting is really what seems to be the best adapted to Ricci flow. So what we've been doing towards this with Julius Baldauf is extending spin geometry to weighted manifolds towards application to Ricci flow. And so we can, for instance, bound the Dirac operator by Perelman's functionals, and we get some information about weighted ADM mass as well. And what's important for us is that the index of the usual Dirac operator is the same as the index of the weighted one. So that's a covariance of the Dirac operator that tells you that this operator that seems to be better behaved with respect to Ricci flow because it's a weighted object is actually giving you exactly the same information as the usual one. And so you might as well follow this operator on Ricci flow and maybe get better information about the index. And so similarly with Keaton, we are also looking at a weighted notion of this D plus D star and hopefully finding the same information. And what's maybe important is that the watchstar commutes with this notion of weighted operator we introduced, and so it will also be adapted to the self-duality I've been talking about in the second part. And so to talk about how this can be used towards this conjecture, well, so the conjecture is really about computing these two indices and understanding what they do at finite time singularities and in the long-term behavior. So what Ricci flow, what has been proven for Ricci flow is by Bamler is that at the finite time singularities you have these orbifold solitons, and at the long-term behavior you have these orbifold Einstein metrics with cusps, and in the thin regions you'll find some collapsed Einstein metrics. And so it's only in a weak sense, but that's what's known, and it's not in a strong enough sense to compute any kind of index. But with Alix, we are starting the second part of the story, which would be gluing perturbation towards reconstructing the degenerations. And obviously, this is very far from bridging the gap between this very weak notion of convergence and this very strong construction. And so the next step would be to, again, bridge the gap between a Gromov-Hausdorff, not Gromov-Hausdorff, but F convergence degeneration and these very, very smooth degenerations. And so this would be very important because having a smooth enough convergence would let you compute, hopefully, these indices and would let you understand these V2 and the signature towards maybe obtaining this target inequality. So yeah, this is all very long term, but we have some tiny progress towards this in this upcoming paper. But thank you very much for your attention.
Are there questions or remarks? Could you say more about this obstruction when you glue this Gaussian sum to S format the two or on the manifold when you glue can you see that it doesn't have an Einstein metric with the Hitchin-Thorpe inequality, or it's something more subtle?
No, so it's more subtle. So it actually, it satisfies the Hitchin-Thorpe inequality. It actually satisfies the same Hitchin-Thorpe inequality as the quotient of the sphere that has an Einstein metric. And actually in some, so I don't know but if you glue in the right orientation, the two Einstein metrics, then actually your topology is exactly S2 times S2. So it carries an Einstein metric. It actually carries an Einstein metric, but it doesn't carry one that's close to S4 mod Z2. So yeah, if you glue them in the right orientation, then your topology is really S2 times S2. And so, you have an Einstein metric there, obviously, and but not one that can be close to this orbifold. So yeah, it doesn't come from Hitchin-Thorpe.
At the beginning, you outlined a sort of a dream approach to the 11/8 conjecture. Can you just explain that again? Because I don't think I quite followed.
Yeah. Right. Okay. Yeah. So it's a strategy that Banner told me about. But the idea is that, so maybe the thing that we cannot hope to achieve in a reasonable time is the classification of Einstein metrics and of Ricci solitons. That's something we don't hope to be able to do in the next 50 years. And so that's what we want to bypass. And so and it turns out that there is a strategy towards this conjecture that bypasses this classification that looks like this. So you have two stages. You have finite time singularities, and so you will be cutting some parts of your manifold and maybe replacing them by some simpler topology. And so Bamler and Chen have a good idea of what to do at finite time singularities. And the point is that what you're getting rid of as positive scalar curvature. And when you have positive scalar curvature, the index of the Dirac operator has to be 0 by this Lishnovich formula. And so you know that the index will automatically be 0, maybe up to boundary terms that we need to understand, but that's at least these parts from just the positivity of the scalar curvature should be fine.
I mean, you could potentially be changing V2 as well.
Right. Yeah, but But I think that by the just some by some just how B2 and tau are modified, you're always going to be in the right direction. Because I mean, both of them are kind of additive when you cut along the right up to boundary terms again, which are one of the problems. This will be additive, and so this will only go in the right direction. Because these parts will satisfy the boundary, the inequality, and so and the remaining part hopefully will also satisfy it by this other argument that in the long-term behavior you will see the thick Einstein pieces, and you should see also some collapsed Einstein pieces, which all satisfy a better inequality than the 11.8 conjecture.
So the topology better change though, because there are things that sit right on the equality line. So
K3. I don't know if there are other topologies that would satisfy the equality.
There might be exotic structures on K3.
Yeah, that's right. But I don't know. Yeah, so that's also one thing that we are asked a lot by topologists is what happens to this one, exotic K3 along Ricci flow, and that's very hard. And so actually I've mentioned, but in the end, in this spin geometry application, well, Julius Baldorf been extending our spin geometry observations to Seiberg-Witten equations along Ricci flow in a weighted setting, and he's used it to show that if you have a Ricci flow on an exotic K3 surface, then it has to develop singularities in finite time or infinite time. So that's one thing you can say, but you cannot say that much. But Ricci flow sees the exotic structures somehow. And so then hopefully all of the pieces will satisfy the inequality. That's what we're saying. So you're cutting pieces that will, so these will satisfy it, obviously, because B2 will be something, can be 0, can be positive, but you will be adding, in the end, you want to glue all of these pieces back together, and this will be additive. And so in the end, you just want that each piece satisfies the inequality, and hopefully that the boundary terms are not too bad. And so maybe the key point really that gives us any kind of hope is that we don't need to understand the Ricci solitons, because we hope to only understand that they have positive scalar curvature and their boundary terms, so their behavior at infinity. And Bamler showed that they are either cylindrical or some cones over some manifold with positive scalar curvature, and they know how to deal with them. They know that they can replace them by some expanding soliton. You cut. It's maybe complicated topology, but which satisfies your inequality, and you replace it by something that's simpler. In some sense, I haven't quite understood. I think that they just get something that has a simpler B1, or I don't remember what they local B1. So I don't really know what they do, but they get it's not been published, so they just thought about it somewhere. Hopefully that's what we're using only. That you have positive scalar curvature, and here that you have the Hitchin-Thorpe inequality, and the rest will really be about understanding the degeneration and not the classification.